Hi physics students, so this is the answer key for the Unit 6 review worksheet for sounds and waves. Here is a long list of all the vocabulary words you want to make sure to know before you go into this test. And then I'm going to go straight into the next problems on this worksheet. So first of all, it says to use a centimeter ruler. Obviously, I won't be able to hold a ruler up using this by screen sharing here. So what I'm going to do is just talk about all the different ways you can measure a amplitude and a wavelength. So for the amplitude, you can go from crest to equilibrium, or you can go from equilibrium to trough. No matter what method you choose, you should get a measurement of about 1.4 centimeters. For the wavelength, you can use many methods. One would be from crest to crest, trough to trough, and equilibrium out to equilibrium. And you do want to know how to measure all those values. That wavelength is equal to 1.3 centimeters or something close to that. In the next question, you've got 60 cycles per second, and it travels 30 meters in 1 second. So what is the wavelength? Well, a cycle per second is the definition of frequency, and it is the number of times a wave passes, or a cycle repeats, or it oscillates per 1 second of time. And so this is our frequency with a unit of hertz, and it travels 30 meters in 1 second. So this distance over 1 second is representative of velocity. So 30 meters per second. Now we have to find the wavelength. So the wavelength, I'm writing out my givens, and my equation using all these variables is velocity equals wavelength times frequency, which therefore means that wavelength is equal to velocity divided by frequency, and that's 30 meters per second divided by 60 hertz. That's going to give us 1/2. And I know hertz doesn't seem to cancel out, but hertz is really 1/seconds, which ends up canceling this seconds in the numerator, so you end up with 1/2 meter. Okay, if the frequency of a certain wave is 10 hertz, what is the period? So frequency is 10, period is the unknown. There is an equation for that, which is frequency equals 1/period, or if you want to rewrite it, it would be period equals 1/frequency, which is 1/10, and that gives me 0.1 seconds. A series of ocean waves with a wavelength of 20 meters, I'm going to write that down, 200 meters, passes a lighthouse at a rate of 1 wave every 12 seconds. So anytime I see waves over seconds, that's a frequency. So 1 wave over 12 seconds, or 1/12 hertz. How fast are these waves traveling? We're looking for velocity. Again, it's our velocity equals lambda frequency equation. And so I'm just going to plug in my 200 meters and 1/12 hertz. And that gives me a velocity of 16.6 meters per second. Again, hertz is a unit that can be converted to 1/seconds, which we don't generally use fractions of units, but it makes it easier to kind of reduce your units if you decide to change it to 1/seconds. Okay. The next question talks about a P wave, and a P wave is an earthquake wave, and a definition you definitely want to know, even though it might not be relevant to this problem, is the fact that a P wave is a longitudinal wave, and an S wave is a transverse wave. And I always like to think of S as the shape of a transverse wave to help me memorize that. So the P wave has a wave that is 5 kilometers per, a wave speed of 5 kilometers per second. So that's my velocity through a solid rock, and it has a wavelength of 150. What is the frequency? So this is gonna, again, be our velocity equals lambda frequency equation. Frequency is then equal to velocity divided by lambda. And 5 kilometers per second needs to be converted. So let me go back and convert my kilometers per second to meters per second. So I'm going to move this down here. When I'm converting kilometers to meters, kilometers is a big unit, which means I need more meters to fill it, and I have to multiply that by 1,000, which gives me 5,000 meters per second over 150. So 5,000 meters per second all over 150 meters, and that equals 33.3 hertz. Generally, you want to keep everything in meters. For waves, you can keep it in kilometers as long as everything else matches kilometers. So if you decided to convert the 150 meters to 0.150 kilometers, that would work out just fine too. Again, S wave is a transverse wave because the S shape looks like a transverse wave. It has the same frequency, so the frequency is going to be 33.3 hertz. It has a speed of 2.8 kilometers per second. What is the wavelength? Since I used meters the last time, I'm going to convert this to meters, and that would give me 2,800 meters per second. And I'm solving for lambda here. So velocity equals lambda frequency. Lambda equals velocity over frequency. I get 2,800 kilometers per second over 33.3 hertz. And that simplifies down to a wavelength of 84.1 meters. All right, that was a lot of calculation. We have one more. Both ways travel to a city 2,000 kilometers away. So this is a distance. It's not a wavelength, it's a distance. And so, and it says how long, which is time, will it take each to arrive? Well, we've got a velocity, a different velocity for each of them. So let me use different colors. I'm going to use for the P wave, the velocity was equal to 5,000 meters per second. And because we have distance and time rather than lambda and frequency, I'm going to use the equation velocity equals distance over time. And so if I solve for time here, time is equal to distance over velocity, and that gives me 2,000. This is in kilometers, so it's actually 2 million meters over 5,000 meters per second. And that gives me a time of 400 seconds. I'm going to use this same equation, but I'm going to plug in the velocity for my S wave. So this is my S wave. My velocity for my S wave was 2,800. So time is equal to distance, same 2 million meters over a velocity of 2,800 meters per second. And that gives me 714 seconds. And as we know, P waves are longitudinal waves, which will always move faster than S waves. So I want you to be very careful with problems like this. Students always think that they have to stick to the speed of a wave equation, which is lambda frequency, but we're not given a wavelength here, we're given a distance. So this goes back to our kinematics equation from Unit 2. All right, this is more conceptual here rather than calculations. At the right of the diagram, sketch the wave, how the waveform would appear when the two waves meet, and then make a sketch of the pulse once they have separated. This image isn't very clear, but what it's showing or supposed to show you is a big wave and then a smaller wave about half the size of the big wave. And so as they approach each other, when they're at the same position, I'm going to use my red pen, their amplitudes are going to double. So since this hits the first level and the second wave hits the second level, if I add them together, they're going to end up a little bit higher than those first two lines. And then the pulse after meeting, I'm going to have the smaller pulse go through the bigger pulse. And so it would look like this. Now, one thing I want to emphasize is reflection, because we didn't talk about reflection much. If I have a wave traveling in this direction and it hits a fixed end right here, the wave is going to bounce back on the opposite side because it always inverts if it hits a fixed point. So in a lab experiment, a student produces a standing wave of 25 hertz on a string that is 1 meter long. So this is the length and this is the frequency. This wave has 2 nodes. Draw a picture of this standing wave, then predict the next 3 standing waves. Draw a picture of the wave at each frequency. So it's a string. The key here is the fact that a string will generally have 2 fixed points. So when I draw this, I'm going to have kind of my 2 fixed points there, and for the standing wave, which is the first frequency, I would end up with one node at one fixed end and a node in the other. And you don't need to do this, but I always like to draw the reflected wave for standing waves because standing waves are waves interacting with a reflection. So this only creates half of a wave. And so if this is a distance of 1 meter, that's the length of it, half of a wave is equal to 1 meter. And therefore, if I were to solve this, one wavelength would be the distance times 2. So my wavelength would actually be 2 meters. Predict the next 3 standing waves. So in this type of frequency, in this type of standing wave with 2 fixed nodes, if I continue to have the same length for each one, I'm always going to have to end with a node at the end. So I have 2 nodes to start. I'm going to have 3 nodes in the next harmonic and 2 antinodes. So it always increases by 1. This is going to be 1 wave. I'm going to have 4 nodes now. So 2, 3, 4. Just extend this a little more. And then here I'm going to have 5 nodes. 1, 2, 3, 4, 5. So this ends up being 1.5 waves or 3/2 of a wave. This is 2 waves. And if I know that the string is always 1 meter long, 1 wave is going to be a wavelength of 1 meter. 3/2 of a wavelength is going to equal to 1 meter. Therefore, 1 wavelength is equal to 1 meter times the reciprocal, which is 2/3. So this wavelength is equal to 2/3 of a meter, or 0.67. And then this last one is 2 wavelengths fit in. So if 2 wavelengths is equal to 1 meter, then 1 wavelength is going to equal 1 meter divided by 2, which gives me a wavelength of 1/2 or 0.5 meters. Okay, so one thing you want to know about frequency is that the frequency as it jumps each harmonic is always going to be a multiple of the fundamental frequency, which is the first harmonic. So the other thing you want to know is that frequency and wavelength are inverses of each other. So really quickly, I want to show you that from the first to the second harmonic, the wavelength decreases by 1/2. And since frequency and wavelength are inverses, this decrease by 1/2 will double the frequency from first to second harmonic. So from 25, I'll go up to 50 hertz. Now, the pattern for the next one isn't as easy to see, but if I go from the second to the fourth harmonic, that decreases by 1/2, which means this 50 hertz is going to increase by double, and that's going to be 100 hertz. So in between here, we have this would be the third harmonic. Remember what I told you, that the first harmonic is always going to have consecutive frequencies that are multiples of it. So from 25, I go to 50. The next multiple of 25 is 25 times 3, which is 75. And then 25 times 4 is 100. So this is the first, second, third, and fourth harmonic, which means just multiplying the fundamental frequency by 2, 3, and 4. Okay, moving on to the next one. If you pull the string tighter, will you still produce a standing wave at 25 hertz? Why? Well, if you pull the string tighter, you're going to change the velocity. That's one of the key characteristics that changes the wave speed. So if the velocity changes, then wavelength or frequency have to change. And we know that anytime you change the tightness of a guitar string, you change the pitch. Pitch is directly related to frequency. So by increasing the tension, you increase the speed. If you increase the speed, you increase the frequency. And therefore, the 25 hertz that you started off with before you pulled the string is going to change. It's going to probably increase frequency due to increase in pitch. Okay, so what is the speed of the waves? Well, it is lambda frequency. They should be the same for all of these harmonics, so you can choose any one. But if I chose the first harmonic, it would be a wavelength of 2 meters times a frequency of 25 hertz, and that gives me 50 meters per second. A harpist plucks 2 strings made of the same material, a long string and a short string. Draw a picture of the 2 sound waves. Label areas of high and low pressure. So a long string and a short string basically mean that I can fit a longer wave into the string, especially in the first harmonic. And so if I have a longer wavelength, I have a lower frequency, and a lower frequency means that the sound waves would be a lot more spread out versus a shorter string where we would have a lot closer together frequency due to the higher pitch. So higher frequency. High pressure is a compression, and then low pressure is a rarefaction. All right. If you have any questions, don't hesitate to contact your teachers. Good luck studying and good luck on your test.